We've spent years chasing graph foundation models, but every time we test a new architecture, we hit the same wall. It's impossible to tell whether a model is actually learning from the graph's connectivity or just memorizing the node features. The benchmarks themselves are confounding the problem. A new paper cuts through this noise by introducing a radically simple diagnostic tool, graph invariants. And the results are quietly devastating to how we've been evaluating graph neural networks. Modern graph learning relies almost exclusively on message-passing architectures. You aggregate local neighborhood information, update node representations, and hope the global structure emerges. But this paradigm intertwines topology with features from step 1. If a model performs well, is it because the graph structure contains predictive signal, or because the node features are already doing the heavy lifting? Worse, the community has obsessed over expressivity, usually measured by how well a model can distinguish non-isomorphic graphs, while largely ignoring whether that expressivity actually translates to predictive performance. This paper flips the script. Instead of asking how powerful a model is, it asks a more fundamental question: how much does structure actually matter for this specific task? To answer that, the authors introduce a framework built entirely on graph invariants. Formally, a graph invariant is a function that maps a graph to a real number, and crucially, it remains unchanged under any permutation of the nodes. If you relabel the vertices, the invariant stays exactly the same. Think of them as structural fingerprints. Examples include the Wiener index, which sums all pairwise shortest path distances to measure graph spread, or the spectrum of the normalized Laplacian, which captures global connectivity patterns. More advanced invariants include homomorphism counts, analytic torsion, and even discrete Ricci curvature measures like Olivier-Ricci and Foreman-Ricci. By computing a suite of these invariants for every graph in a dataset, you get a fixed, permutation invariant vector that describes the graph's topology completely independently of its features. The authors then feed these vectors directly into a gradient-boosted tree ensemble, specifically XGBoost. No backpropagation, no message passing, just static structural descriptors and a highly optimized tabular model. Let's look at the first major result. The authors test these invariants on the BREC dataset, a benchmark specifically designed with 400 graph pairs that the one-Weisfeiler-Lehmann test cannot distinguish. Standard message-passing GNNs are theoretically bounded by 1WL, so they struggle here. But when you concatenate a diverse set of invariants, the resulting model distinguishes 73% of these pairs, outperforming nearly all standard GNNs and even some higher-order architectures. Even more interesting, a greedy selection shows that just 4 invariants, analytic torsion, mean commute time, magnitude, and graph radius, are enough to capture nearly the same expressivity. This tells us that global structural descriptors are inherently more expressive than local aggregation schemes, but it also raises a red flag for the field. We've been treating expressivity as the holy grail, yet these invariant subsets achieve high expressivity while being completely non-trainable. But expressivity is only half the story. The authors use these invariants to perform what they call metaclassification, training a model to predict which dataset a graph came from, based solely on its structural fingerprint. The results are stark. Across 23 datasets from domains like molecular chemistry, social networks, and computer vision, a model can correctly identify the source dataset 56% of the time. Filter by domain, and that accuracy jumps to over 90%. Datasets within the same domain aren't structurally homogeneous, they're fundamentally different. This structural shift has a direct, measurable impact on multitask learning. When the authors train a shared GIN encoder on pairs of structurally dissimilar datasets, gradient alignment plummets. The gradients from one dataset literally fight against the gradients from the other. This negative correlation between structural dissimilarity and gradient alignment explains why pretraining on mixed graph domains consistently fails. Foundation models aren't struggling because architectures are too simple. They're struggling because the benchmarks assume structural transferability that simply doesn't exist. This leads to the most provocative finding. The authors benchmark their invariant-based XGBoost models across 26 standard graph datasets, comparing 4 input configurations: raw node features summed or aggregated, the full invariant set, and a minimal expressive subset. The results: on a significant number of tasks, the invariant-only model matches or exceeds transformer and message-passing baselines. On the new flow benchmarks, the invariant approach outperforms the best-reported GNN and graph transformer results by a massive margin. This isn't a call to abandon neural networks. It's a diagnostic tool. When invariants provide no performance gain over raw features, structure is likely irrelevant for that task, and you're wasting compute on a GNN. When invariants combined with aggregated features outperform features alone, you know the model needs to learn structural biases. The paper argues that invariant-based baselines should become mandatory. If your fancy new architecture can't beat a gradient-boosted tree on static structural descriptors, you're either overparameterized, undertuned, or solving a task that doesn't actually require graph reasoning. So where does this leave graph foundation models? The path forward isn't just deeper networks or more parameters. It requires acknowledging that structural heterogeneity is a hard constraint. Benchmarks must be evaluated not just on predictive accuracy, but on structural coherence. The authors lay out a practical protocol. Before training any new model, fit the invariant baselines. Use them to diagnose whether features, aggregation, or global structure is driving performance. If structure doesn't matter, treat it as a tabular problem. If it does, design architectures that explicitly incorporate those structural biases, rather than hoping message passing will magically extract them. This paper doesn't just offer a new baseline, it offers a falsifiable test for graph learning. And until we stop conflating features with topology, we'll keep chasing foundation models that can't actually generalize. If you want to dive into the full methodology, the invariant sets, and the multitask gradient alignment experiments, the paper is linked in the description. Let me know in the comments how you think this changes the roadmap for graph foundation models.